our next speaker, Dr. Babu Fathepure from Oklahoma State University, is our final speaker for today. And he'll be talking about some of his work on bioremediation of produced water by halophilic microorganisms. So Babu, we will turn it over to you.
Thank you very much. I'm going to talk about today the role of microorganisms in bioremediating or cleaning up produced water. When I said microorganisms, I'm talking about special microorganisms. You know that produced water is highly saline. I will show some slides. So you know that also salt kills microorganisms. That's why we pickle like salami, for example. So when you add salt, microorganism will die. So you may ask question how you're able to use microorganisms because microbes will die. Not really, you know that microbes can live in any environment. We're using extremophiles, particularly that organisms survive. In fact, they love salt. We're talking high salinity. I'm not talking about salinity like a marine environment, which is very, just 3%. Our organism can live anywhere between 5% salt, 10% salt, 15% salt, 30% salt. Same time they live and eat hydrocarbons. So I have been working on this from last 10, 12 years. We have microbes, we call them halophiles, and these are specially we enriched from contaminated production sites, also contaminated lakes. They are specialized. They can degrade hydrocarbons as their food are consumed for growth. We have both mixed cultures and pure cultures. Today, I'm going to tell the story about mixed culture and also pure cultures, how we can use them to clean up produced water, at least the first phase, how we can use them to remove organic contaminants, which are toxic, which are carcinogenic. All right. Here is a lot of information. You don't have to read those things. Here is the produced water. I'm sorry, I don't have a source. I found somewhere else I'm using. It has lots of heavy metals, BTX, and NPDs, naphthalene, phenanthrene, and other one. Okay, PHS, polyaromatic hydrocarbons. Make a long story short, you already know it's loaded with very different kind of organic compounds, inorganic compounds, and also radioactive compounds. It's very nasty environment. So at least my part is to remove organic compounds. Both organic compounds involve hydrocarbons, mixture of hydrocarbons. All right. So the produced water also, we know that this previous speaker spoke about that 1 barrel of oil can produce 9 barrels of wastewater or produced water, depending upon the age of the oil well. So there are some estimations, roughly 21 billion barrels of produced waters are generated in USA alone. That's a very huge amount. And unfortunately, there's not much oil wells don't have efficient way of disposal or treating because this is nasty produced water. So we also know more than 90% of the produced water is deep well injected. Because of that, we are experiencing earthquakes. And also this deep well injection can have a potentially dangerous effects on the environment. Maybe while deep well injecting, the pipe may break, contaminate drinking water. There's a lot of problem. So we can we use this water? Everybody's really trying to understand how we can clean up. We can use this water, at least for industry, at least for irrigation or livestock, various purpose. So before you use, you have to really clean up because it is highly complex. as just mentioned here, it requires the use of multiple treatment methods involving physical method, chemical methods, biological method. Being a microbiologist, my role only comes in biological processes where I can use my microbes to eat those organic compounds, which are sometimes carcinogenic even at a very low concentration, like benzene, for example. There are many, many compounds, both aromatic, aliphatic, alicyclic, you name it, produced water has. So today I'm going to tell you some story how we're using our microbes, special microbes that can tolerate very high salt concentration and eat hydrocarbons. Before that, I want to impress upon you this I got from a publication. Particularly, this problem can be very useful for a dry lands. You see the world map here. We have a this is a northern Libyan desert where we have extremely hyper-arid region, not much water available. And we have yellowish, dark yellowish. These are all arid, semi-arid environment where also you can see we can see these are highly, with the round which I marked is oil exploration activity. So we have really a lot of problem here. So projection estimate that half of the global population will live in region with high water scarcity by 2030. This is the United Nations report. And in addition to that, climate change can really projected to increase the water scarcity in these dry lands. So as water resources are diminishing, water users like industry, agriculture, households are competing more and more for access of water. So therefore, there's a pressure on water resources is expected to, in fact, intensify between water users and oil and gas firms. So just to tell you, so we need to, the oil and gas producers make a lot of produced water and use fresh water. So I think it's very important. We need to find ways to reuse the produced water. That is the slide actually take home message. Here in I'm going quickly because I have limited time. My project, which is funded by EPSCoR, we have major 3 objectives. My role comes, the first one here, assess the extent of hydrocarbon degradation using salt-loving microorganisms. So I mentioned what are salt-loving microorganisms. Once we remove organic compounds like hydrocarbons, then we can actually, the next would be removing salt. I'm also collaborating with the engineers. They're trying to come up with a cheaper way to develop ways to remove salt, like a membrane system. All right. And also, once we clean up produced water using bacteria and membrane, we can next, it's important, we need to test the water. Is it still toxicity? So I'm doing all the 3 with collaboration with the engineers and other people here. Today, I'm going to focus mainly on biological processes. Are there any microbes? Can we remove hydrocarbons, which are supposed to be toxic? All right. So this gives you, I have, as I mentioned before, we have both mixed culture, or we call them enrichments. We enriched microbial community for at least this is I got some sample from Kuwait about 6 years ago, from a highly contaminated, highly saline environment. The salinity of the environment was 28% salt and contaminated. I got that sample. We began to enrich microbes that can eat hydrocarbons. It took a long time. We enriched microbes. It became a mixed culture enrichment. We use a molecular tool to address who lives there. We found we got in a highly enriched culture. It can degrade, mentioned here, BTX, polyaromatic hydrocarbons, alkanes, as their food source at salinity from 5 to 20% salinity. This organism can eat all sort of hydrocarbons. It is made up of one dominant person or organism we call we identified is Rhodomonas. Don't worry about the name, but about 98% of the community is dominated by one group of organism, and other members of Clostridium, Bacillus desulfovibrio, Pseudomonas, these form only minor components. These are very stable enrichment. We have been maintaining, periodically transferring to new medium from last 6 years. So what is going on here? They become very stable partners. We did metagenome sequencing. We found what kind of genes are there. I don't want to get into too much of that. We believe the main guy is actually the main one who degrades hydrocarbons and makes some intermediate compounds. And those, the minor satellite population live off that product degraded by the main person here, main guy, main bacterium. Now, what is the advantage of main microbe is getting these guys? We looked at the genes, looks like members of these satellite organisms are providing vitamin K because the main guy doesn't have those genes. So there is interdependence going on. So this is a different story. You're trying to study ecology in the environment, but these community can do a good job for us. They're able to degrade petroleum compounds in salinity ranging from 5 to 20%. That's why we're using. Quickly, we use this kind of microcosm to study what kind of hydrocarbons they degrade, what kind of salinity. We use main microcosm here. We have a synthetic medium. We add BTX from top here. We have a septa here, Teflon coated. We inject BTX. BTX is a volatile compound. Most of the BTX dissolves and some remains in the headspace. We use gas chromatograph of headspace to monitor how BTX is degrading during different time period, different temperature, different salinity. And also we can take this culture and look at other hydrocarbon degradation. These are minor microcosms. That gives an idea how we conduct our research. This organism, I'm going to quickly move on. We use that culture from Kuwait to look at produced water. We got produced water from Payne County and also Wilcox here. Sorry, let me see. I think I have this missed here. Anyway, we tried this organism to produced water, one from Payne County, one from Garfield County. We found one of the produced water is very, very toxic. Unfortunately, the figure is deleted by itself during I was working today. So simply to tell you a story that we add in these microcosms, I just showed you from the top, BTX to see whether this organism degrade. Now here is the, okay, this is the slide I wanted to talk to. It is here somewhere. Grant County, extremely toxic produced water. Some of the information I have given you, TDS is about 346,000 milligrams, salinity to 37,000 milligrams, sodium 68 or 69,000 milligrams. These are the main component. In addition, it has a lot of heavy metals, you name it. So this is extremely toxic water. When we injected our organism in this water and monitored some of these hydrocarbons, as you can see, here is the date, BTX degradation. This is actually a mistake here, micromole per bottle. So instead of millimole, you can see here, none of the compounds are degraded even for a month. So then we felt it's very, very toxic water. Our organism, well, we added to degrade these compounds, dead actually. Later we tried to culture the organism, none of them survived. There is something this water, extremely, extremely toxic. When I looked at the water, it's so clean, feel like drinking, but it's nasty water. We don't know what makes this water so toxic. Most produced water we use are not that toxic. Then the question comes, how can we use microorganisms to degrade these compounds in toxic water? What we did, we thought maybe we can mix this toxic water with another wastewater. So we got, still water, wastewater we got before it's treated. So we mix this wastewater with the produced water from Grant County at different proportion. We found when we mix this water 50%, then we saw all the hydrocarbons degraded just in 5 days. In control bottle, where we don't have microorganisms, it doesn't degrade, suggesting our microbes are able to degrade at least these indicator compounds, BTEX, when we mixed, as you said here, and we mentioned 50% produced water from Grant County, 50% by volume, okay, wastewater, we're able to show. So the take-home message is that if you have a production site where it's producing extremely high concentration of very toxic produced water, we can still use our microbes, but you have to reduce the toxicity by mixing with other wastewater. We're able to show we can actually treat two different kind of wastewater. You may ask, where do this has been already going on in Brazil. They're trying to mix their wastewater with the produced water, and there's a huge reactors that are able to clean up produced water. Okay, that's one take-home message. So again, our microorganism can live in toxic produced water if we can dilute it. All right, so moving on. Another one, we try to use our organism to see whether it can clean up produced water. This is from Payne County. This water is not very toxic. Here is some major component of that. TDS is all the way half what we saw in Grant County. Sodium chloride, okay, it's not very toxic at all. So when we used our organisms, we're able to see all the benzene, toluene, ethylbenzene degradation within like 9 days straight in produced water. And he's in a control bottle. When we don't add our organism, BTX will not degrade. So suggesting our organisms are able to munch on those, eat those compounds and remove them. We also tried mixing this our Payne County water with 50% wastewater, slight improvement. Instead of 9 days, it took about 7 days. So again, take-home message is, mixing can be done effectively. If you find the produced water is very toxic, we can use microbes to clean up. Moving on, this is about using our cuvette culture. Now I'm going to talk about something else. We also isolated recently, a pure culture from Wilcox produced water. Here in Payne County, we got that. We isolated actually a pure culture, and later we published this paper recently and identified using molecular tools. We found this organism named as very closely related. This organism, our organism, is very closely related to somebody isolated in Tunisia. Tunisia, people have isolated from production sites. They identified it as a Modicicalibacter tunisiensis right here. And our organism, when looked at the genome sequencing, it's very closely related. Our organism is here, Modicicalibacter species, strain Wilcox. We named as strain Wilcox. You can see here, genetically very closely related to the organism that was isolated at Tunisian produced water. Now we have pure culture. We can do a lot of good stuff. We can look at how it grows. We can study its metabolism, pathway of hydrocarbon degradation, and also genes. We genome sequence this organism to see what kind of hydrocarbon this organism can eat and what salinity it can grow. So that's what we have done. We use genome as a, a guide to study its living style, what kind of chemicals it can degrade, what salinity can live. So some of the results I'll show you. Here is this organism, pure culture, can degrade BTX. Here is in control, no degradation. Obviously, we don't have our organism. This is the xylene degradation profile. It took a long time. At high salinity, this is about 2 molar salt, which is 15% salinity. Xylene takes about 21 days. And other compound, like here is the ethylbenzene goes quickly within 7 days. Here is the benzene goes away in 7 days. Here is the ethylbenzene goes. So except xylene, other compounds are degraded within a week at 15% salt. This organism can eat this compound, completely degrades. We're talking about complete mineralization. We're not talking about converting BTX into another form of compound. We're talking about complete destruction of the compounds. Okay. Moving on, we also use this organism. I'm not going to show all the data. It can use benzene, toluene, ethylbenzene, xylene, phenol, benzoate, phenyl acetate, they degrade. And we found genetically genes are there for all of these compound degradation. We can validate the genes are active and degrade all these compounds. In the laboratory, we showed genes for all these compounds are there, complete metabolic pathway. You may be wondering, maybe one gene for benzene, one gene for toluene. No, benzene degradation is, for example, it has 19 genes to simply degrade. Benzene become phenol, then become catechol, then variety of pathway it goes through, all the way become acetyl-CoA, that goes to TCA cycle. That's why they live. So it's not that simple. We have complete pathway for all of these compounds genetically, and also really does that. In addition to that, it grows in biphenyls, degrades completely, but it doesn't have genes for naphthalene, phenanthrene. When we added in the bottle naphthalene, phenanthrene, it didn't degrade. So again, the genetic information will tell you what organism can do. It doesn't degrade methane, it doesn't degrade hexane, but degrades decane, which is 10 carbon long aliphatic compound, degrades hexadecane. So, this gives you some idea, snapshot of this organism's potential to eat different compounds. Moving on, this slide shows you, we have also tried to understand its degradation of hydrocarbons, especially BTX. We use a different salinity. This gives the rate of benzene BTX degradation. We saw actually normal optimum degradation occurs at most of this compound degrade optimally rapidly at 1 molar, which is 6% salt. And this is the salinity. It can degrade even up to 4 molar. BTX takes about 60 days to degrade at 4 molar. 4 molar salt is, we're talking roughly 25% salt. Okay, so this organism can degrade hydrocarbons at varied from very low to very high concentration. No degradation of BTX at 0 salt. It requires salt. It's a halophile, salt-loving organism. Okay, moving on. We also tried to look at real, this is just to show you quickly, can we take this organism, bring the produced water, simply dump it, don't add anything, simply add to the produced water. And it does. In fact, you can see this one is simply to show you control, no BTX degradation. Xylene did not degrade in real BT produced water from Payne County. And other compound undergo degradation. We didn't give any nutrients, nothing, no pH adjustment, simply took it to natural produced water, added to that, it does degrade benzene, toluene, ethylbenzene, no degradation of xylene. Okay, these are compounds were tested individually. When we mixed with the BTX together, okay, then try all of the compound degraded, even xylene went away. So assume that the genes that are induced for the degradation of benzene or toluene or ethylbenzene attack the xylene. So when you mix this compound together, even xylene is gone, okay? I think I'm sorry, I'm really going fast because of the time. So you're always welcome to answer. When we looked at the genome, we found it has lots of mechanism to survive, tolerate different kind of metals. Okay, we have an enzyme system, we have efflux pump. It has genes to make efflux pump, means, just to give an example, when you give antibiotic to certain bacteria, they will leave. You know why they leave? Because as soon as you add antibiotics, The efflux pumps take the antibiotics, spit it out, throws out. As a result, organism will not be killed by antibiotics. Same way, this organism has a lot of efflux pumps for copper, nickel, cobalt. We're still testing arsenic, selenium also. It can lead, it can survive. These are experimentally, we're trying to see, because genome tells it has efflux pumps or copper, nickel, cobalt, zinc, arsenic, selenium. Really, what is the concentration it can survive? We set up microcosm using different concentration of copper. We set up microcosm, different kind of nickel, different concentration of zinc. We found this organism, this work is going on right now. We found copper can be toxic about 250 micromolar. Nickel can be toxic for 100 micromolar. Cobalt for 100 micromolar. We were so surprised it could live and degrade BTX and survive even at 7,000 micromolar. Zinc is very, very resistant for zinc. We are now trying to address how can it live in such a high concentrated presence of zinc. So we are going to test its mechanism, what it's doing. 7,000 is 7 millimolar, which is 0.1%. I have not heard microbe living at that high concentration. We're going to explore its ability to survive at high concentration of zinc, what mechanism it has. It is a very recent experiment. We're still looking at chromium, cobalt we have done, and I will try to test lead and arsenic. It has genes for those compound resistant genes. So actually, experimentally, you can see that here. Now, here is the overall bigger picture. How can we apply our microbes to treat produced water? Okay, we have a reactor here. We have produced water. We can add our microbes here. Now, before you add, we have to have some kind of a smart system to determine the toxicity. If it's not much toxic, directly we can treat the water. If it is toxic, then we can add wastewater right here and try to reduce the toxicity. What kind of smart system, we don't know. We're just, it is our this sort of model. There could be many analytical method that can analyze produced water, which is coming into reactor. If it is highly toxic, then mix with the wastewater, reduce the toxicity, then degrade hydrocarbons. Once hydrocarbons are gone, the next goal is to remove salt. Here is the
you've only got like 1 or 2 minutes left. Sorry to cut you short.
Yes, I'm done. I'll be done.
Oh, no. You can wrap it up.
Okay. Now, after bioremediated, now we have to worry about salt. We can use certain cheap membrane system. Before that, you remove solid, add lime. Once you do pre-treatment, pass that bioremediated produced water through membrane, you remove salt. We have done that. Here is the treated produced water. You can analyze for anything. BTX is there still. So what is the salinity? Everything you can analyze. If they're all gone. We also tested, after passing through membrane or water, we have done some experiment. We treated our hydrocarbons with microbes, treated with membrane. The produced water was treated, we tested with the toxicity using Daphnia. Commonly, Daphnia is a water flea. If the water is very toxic, it will die. So this water, when we tested Daphnia, is dead. We thought, what is going on here? But later found out our water is so pure, is almost like a distilled water. Distilled water is not good. If you drink distilled water for a few days, you'll be dead because you need salt. So we added salt back. So what I'm trying to do is we can use this technology to remove hydrocarbons. We use this technology to clean up produced water, really. So we cleaned really very bad. In fact, we can add salt back, then the Daphnia survived. Okay, now we can use the treated water for growing switchgrass. Switchgrass can be used for making biofuel, or you can use for industries as a cooling tower coolant. You can use as a fracking. So this is the strategy we are proposing, and we have done that. We can clean up the water. Okay, here is the Daphnia. I'm not going to go over its time. So just to tell you what the last figure, slide, why is our approach is important? Because we can use microorganisms to degrade contaminants. So you use microorganism is a natural process. You can produce environmentally sound and sustainable process. We use hydrocarbon degrading salt loving organisms because any other organism will not survive for bioremediation. Toxicity can be reduced by mixing other wastewater. So two types of wastewater can be treated. Okay, we can use a different membrane system. So essential for cost-effective desalination. Use this remove salt using cheap membranes. Then basically you can test the toxicity after these two process. If the tax is not very toxic, then we can use this for suitable that water for reuse for various purpose. All right, this is an interdisciplinary process, so we can generate, help train students and everything. So this is a quick way of telling we can use microbes and membrane to treat produced water. Okay, this is my last slide. Oh, one more slide I have. Sorry.